Okay, this is a continuation of today's lesson. Just going to do another few examples. Function here, y equals x squared plus 4x minus 3. Now we know that that is a concave up parabola. So we know that it is not a one-to-one function because it's concave up. There will be a decreasing and an increasing part of the curve. So by restricting, first we're going to restrict the function to a monotonic increasing function, write down its domain and range, and then find the inverse function of that. And we'll also then restrict it to a monotonic decreasing function and find the domain and range of that corresponding inverse function for that. So here is our original function of x equals x squared plus 4x minus 3. Okay, I'm just going to do a very quick sketch of that function over here. If I factorize that, I've got x, a little bit hard to factorize because the factors of -3 that add up to 4, can't really find those. So what I'm going to do instead of that, just to have a quick sketch so that you can see the original function, why don't we work out the axis of symmetry? X is negative b on 2a, which would be -4 over 2 times 1, which is -2. So the axis of symmetry occurs when x is -2. And when x is -2, we can find the y value. So y is -2 squared minus 8 minus 3, which is 4 minus 11, -7. So we've got -2, -7 as our vertex. We know that it's concave up and it cuts the y-axis at -3. So basically this is our parabola. Okay, we know it's concave up. Axis of symmetry here at x is -2. So we're going to restrict the domain. So for the function of x, if we restrict the domain, let's look at the monotonic increasing function first. So looking at this one, if we restrict the domain to, so our function of x is y equals x squared plus 4x minus 3. If the domain is just from here onwards to make it monotonic increasing, so if it's x greater than or equal to -2, then the range of that function, what are the y values? They are y is greater than or equal to -7. So restricting the domain to monotonic increasing will give us the domain is x is greater than or equal to -2. The range is y is greater than or equal to -7. So therefore the inverse function, which we need to work out what it is, so I'll just do that down here. So for the inverse function, we know, remember we're changing the swapping the x and y values. We've got x equals y squared plus 4y minus 3. Now we need to make y the subject. So let's take this -3 over, adding 3 to both sides. We get x plus 3 is y squared plus 4y. Now what we want to do is to complete the square on the y. So we get y squared plus 4y plus, now half of 4 is 2, so plus 2 squared. And add that to the other side as well. So x plus 3 plus 2 squared as well. So that gives us y plus 2 all squared is equal to x plus, now 3 plus 4 is 7. Square rooting both sides, we've got that, and I'm going to swap sides as well. Y plus 2 is plus or minus the square root of x plus 7. And making, so square rooting both sides, therefore y is plus or minus the square root of x plus 7 minus 2. Now, we need to see if we restrict this to the monotonic increasing function. I'm just going to draw that one there. Which of these will it be? Positive square root of x plus 7 minus 2 or the negative square root of x plus 7 minus 2? Well, we'll be able to tell which one it is by looking at the domain and range of the inverse function. Monotonic increasing part of the function, we've got this point down here, -2, -7, and this point here, which is 0, -3. Now remember that I haven't drawn this very well, but just by swapping the x and y values here, we'll be able to tell which of these functions here, the positive square root of x plus 7 or the negative square root, which of those will be the one that will be the inverse function of our monotonic increasing function. Now 0, -3, swapping those around, we've got -3, 0. So here, this point relates to this point, and -2, -7, its corresponding position in the inverse function will be -7, -2, so roughly about there. Okay, and just trying to see where this point's going to be. I don't think we can. So it will look like this. And wherever this one crosses y equals x, this other one should also cross y equals x. Now, the other thing we can see is, for example, when x is 2, so the other thing, this probably is the quickest way now once we've drawn it, when x is 0, has to be the positive value. So when x is 0, we'd have to have positive square root of 7 minus 2. Now square root of 7 is greater than 2, it's almost 3. So when x is 0, we need a positive value for y. So therefore, the inverse function is going to be positive square root of x plus 7 minus 2. We can tell that by drawing it. The other thing we could also do is substitute in when x is -3 here. So when x is -3, we get -3 plus 7 is positive 4. So square root of 4 is 2. The only way that we're going to get -3, 0 is for positive 2 minus 2 is 0. So this again has to be the positive. So I can either draw it, I can substitute the point in -3, 0 into this plus or minus equation, and I need to get 0, and I'll see that if it's the positive square root of x plus 7, I will get 0. I won't get 0 if it's -2 minus 2, that would give me -4. Okay, so it has to be the positive square root. So therefore the inverse function is y equals positive square root of x plus 7 minus 2. Now if the domain of the original function, which is restricted to monotonic increasing, is x greater than or equal to 2, therefore the range will be y is greater than or equal to -2, and we can see that, and the domain will be x is greater than or equal to -7 for the inverse function, and we can see that as well. Okay, right, we're going to do the same with the monotonic decreasing function. Monotonic decreasing function, we know that the inverse of the increasing one was the positive square root of x plus 7, so therefore that's the inverse relation. So therefore the inverse function will be the negative square root of x plus 7 minus 2. Now what we're going to do, we're just going to see that that is in fact true. Remember, for the original function, so here's my original function, remember that the domain was this is for the monotonic, so this is for the monotonic decreasing function. Sorry, we didn't work this out yet. So for the monotonic decreasing function, the domain x values are x is less than or equal to -2, and the range is y is greater than or equal to -7. So therefore, for the inverse function now, so that's the inverse relation, this is the inverse function here, the domain will be x is greater than or equal to -7, and the range will be y is less than or equal to -2. We can also draw the inverse relation of function. There is negative x value 0, so the inverse function will be 0 and some negative y value here. So this function is going to, if I actually turn it sideways, I can probably draw the inverse function a bit better. Just like, oops, not drawing it very well, but something like that, okay, where it's reflected in this line. Probably should come out a bit more actually, okay. So there's my inverse function there. Okay, now if that's, so this is the point -7, -2. Okay, graph's not looking that great. I'm sure you can draw a better one. Just make sure that they intersect on the line y equals x. That's really important. Okay, and it's there. All right, so let's just have a look at this domain. Is it x is greater than or equal to -7? Yes, it is. And is the range y is less than or equal to -2? Yes, it is. So it goes more like this. I probably haven't done a very good job of drawing this original one. It should go like that. Okay. So just stressing that point again, just a really important thing is that these cross on the line y equals x, okay? And that whatever this x value is here, for example, if that was -4 or something, but it's not, that would be the same y value down there. If this was, say, -4, 0, that would be 0, -4. However, I haven't determined this value here because this function is not an easy one to factorize. We could use the quadratic formula if we wanted to find this particular value of x. Actually, I do have this value here with this inverse function, because when x is 0, I've got -7, which is something like just maybe -2.7 or something like that, -2, all right? But I'm not going to write exactly what it is. We will draw these properly. So even though we couldn't factorize it, we can just substitute values, of course, just sometimes forgetting the really basic things. So I've just put a few points here, -2, -7, -4, -3, and -5, 2. So just swapping values around, we'll have 2, -5, which will probably be about here. We've got -4, -3, which will be -3, -4. And of course, I haven't drawn this very well again. And -2, -7 will be -7, -2, -7, roughly here, -2. So just trying to draw that again, something like this. I think it looks similar to what I had. Okay, and make sure that there's a dot there because that's actually where it starts from. So -7, -2, and you can just label some of these other points. This would be 2, -5. Okay, and again, make sure it's cutting on the line y equals x. Another property of functions, another property is that dy dx times dx dy equals 1. So we're just going to show that property for this particular function, y equals ln x plus 1. So if you forget how to differentiate that, of course, you would refer to your formula sheet. And the derivative of ln x is f dashed x over fx. Now fx, so that is the derivative of the log of the function of x. That's how you do that, just getting that off the formula sheet. So differentiating what's inside the bracket, you get 1 over x plus 1. So that's what dy dx is. Now, to work out dx dy, I'm not going to just flip that. What I need to do is to change the subject of this formula to x. So if y equals ln x plus 1, and if we want to change the subject of the formula to x, we'll need to get rid of the ln. Inverse operation is e, so e to the y equals e to the ln x plus 1. So therefore, e ln cancels, so therefore x plus 1 equals e to the y, which means that x equals e to the y minus 1. So now we're going to find dx dy for that function. So dx dy is, now if you differentiate e to the y, you just get e to the y, and if you differentiate a minus 1, you get the constant 0. So now we can look at dy dx times dx dy. Now with this e to the y, we're going to write that now in terms of x, or you'll see why I'm going to do that down here. So if dy dx is 1 over x plus 1 times dx dy is e to the y, obviously I really can't do much there. Here we can see that e to the y, you can either substitute straight the e to the y is the x plus 1, or you can put it as x plus 1 times e to the, here, ln, y is ln x plus 1, which is 1 over x plus 1 times e ln cancel times x plus 1. Of course, that's in brackets, and it's on the numerator, so I'm going to put it over 1. The x plus 1's cancel, and I'm left with 1, which is the result that we're trying to prove, that dy dx times dx dy